Okay, welcome back. What I want to do now is continue with session 3 of AC motors, various types and utilities and applications. Okay, now here, definite and special purpose motors. Now, definite purpose motors handle specific applications and have well established NEMA standards. Okay, that's the organization that sets the standards for motor production, etc. Okay, look it up yourself. Don't just take this as read. Okay, now they are produced in high volume and are low in cost when compared to general purpose motors with the same ratings. To apply a definite purpose motor for a duty other than that for which it was intended must be carefully considered. Okay. The modifications can be made easily and inexpensively. Other modifications may require special tooling, increasing cost. The electrical characteristics of the motor must be checked very closely against the load. Testing the motor with the application is recommended. Now you don't want a motor that's going to be burning out or straining to lift a given load or to rotate a given machine. Okay, because if the machine is too heavy, excuse me, if the load is too heavy for the motor, then you're going to cause massive problems and your motor will not be lasting very long. Okay? Now instrument motor definitions vary with the users and manufacturers of motors. Generally, an instrument motor is a precision motor with fractional or subfractional horsepower ratings. Sizes range from 1/2 horsepower to 3/4 horsepower. Okay, gear motors. A gear motor consists of a gear reduction unit with an integral or flange mounted motor. Now, what this gear unit does, it allows the motor to run at a given speed and allows you to control the speed of the motor through a gearing system. Okay. The main advantage of a gear motor is that the driving shaft may be coupled directly to the driven shaft. Belts, pulleys, chains, or additional gearing to step down motor speed are not needed. Also, coupling or belting of a motor to a separate speed reducer unit is eliminated. Torque requirements. Now, torque requirements. Starting and running torques are considered separately because starting characteristics of the motor and gearing differ. Applications needing high breakaway torques require careful selection of the motor because split phase, polyphase capacitor start and brush type motors have large starting torques. Okay. Now just let me remind you that this is session 3 of various types of motors and applications. Okay. Applications with high inertias should be analyzed by the gear motor manufacturer. This problem is critical with self-locking right-angle gear motors, since rotor and load are rigidly connected by the gear train. Both must stop in the same time. In severe cases, momentary power failure may be all that is necessary for a high inertial load to destroy the gear train. Overhung loads are applied to the output shaft of the gear motor whenever the gear motor is connected to the application requiring cams, belts, or gearing. Now, some of you will be a lot more familiar with this because some of you will actually be dealing with motors that drive a belt or chain or a pulley of some sort. Okay. Application requiring cams, hoisting drums, or switches at the output shaft can also cause very high overhang loads on gear head bearings. It is inherent with gear motors that overhang load capacity decreases as the delivered torque increases. This reduction is caused by internal gear reduction forces. In small horsepower geared heads, or FHP gearheads, reducer bearings may be fully loaded by the reactions resulting from weighted torque. Under these conditions, no additional overhang load may be placed on the output shaft, because this will cause damage to your motor and will give the motor the impression that it's driving an excessive load. When the overhang load capacity of a gear motor is too small, it may be possible to obtain oversized shafts and bearings. A third or outboard bearing is sometimes used to support the end of the drive shaft. However, it is extremely important that this bearing is properly aligned to prevent excessive shaft and bearing loads. Thrust loads are most severe with vertical shaft units and gear motors. Driving a lead screw or axial actuating device. It is often less expensive to specify a heavy-duty unit rather than extensively modify a normal duty unit when loads are excessive. Toothless motors. Some motors can be made with toothless armatures thanks to powerful modern magnets. Coils are wound and assembled outside the motor, then inserted and secured as a unit in the armature. Toothless construction provides more space for armature coils and provides higher current ratings. Iron losses are cut by 50% and armature inductance approaches that for cup motors. Toothless motors do not cog at low speed, and because coil insertion is easier, motor diameters can be smaller. In toothless motors that use ceramic magnets, flux density in the air gap is much lower than in conventional motors. Okay. The low density results from the large air gap, an inherent characteristic of toothless construction. Toothless motors equipped with rare earth magnets, however, operate at high flux densities. These motors contain magnets that are about the same length as the air gap. With this relationship, rare earth magnets operate at flux levels that are close to the magnet's maximum energy product. Let me just go back a little bit, make sure that we got everything in, okay? And that you can look at this at your own leisure. You can show that Look, just making sure that I right, let me just go back and make sure that I know where I am at. Okay, so back to motor starters. Just want to make sure that I got everything in and it wasn't out of frame, out of shot. Okay. Okay, I think we're there. That's about it. Okay, I think yeah. Okay, thank you. Alright, and then we come to motor starters. Okay, right. Motor starters. Now, full voltage, single speed motor starters. Single speed squirrel cage motors have starters that fall into two categories: full voltage or across the line starters and reduced voltage starters. Now, full voltage starters, manual and magnetic, apply full voltage directly to motor terminals. Two other types, combination and reversing starters, consist of a starter, usually magnetic, with added functions. Reduced voltage single speed motor starters. Some machines or loads may require a gentle start and smooth acceleration up to full speed. In addition to load demands power, company regulations may limit the current surge or voltage fluctuation that can be imposed on the power supply during motor starting. Many starters apply reduced voltage to motor windings, primary resistor, primary reactor, autotransformers, and solid state. Part winding and Y delta starters can also provide reduced voltage starting, although technically they are not reduced voltage starters. Multi-speed motor starters. Motor windings in multi-speed squirrel cage motors may require special starters. Starters for separate windings two-speed motors consist of two standard three-pole starter units that are electrically and mechanically interlocked and mounted in a single enclosure. Additional units can be used for each speed. Although these are always electrically interlocked, it may not be practical to provide mechanical interlocks on more than two starters. The starter for a consequent pole two-speed motor requires a 3-pole unit and a 5-pole unit. The design of the particular motor winding determines whether the fast or slow speed connection is made by the 5-pole unit. For 3-speed consequent pole motors, a 3-pole starter is used for the single speed winding. A 5-pole starter and a second 3-pole starter handle the reconnectable windings. A 4-speed consequent pulse motor requires two sets of 3 and 5-pole starters. Again, do a bit of additional research for yourselves so you can actually see some of these in practice, okay? What they look like photographically. Different power circuits are needed for delta type multi-speed motors because currents circulate within the inactive or unconnected windings. A pair of 4-pole starters is required for a 2-speed motor with separate open delta windings. Another 4-pole starter is required for each speed, thus 3 and 4-speed. Motors with open delta windings require very complex starters. Specific windings information is used to select the motor controls. Torque characteristics also deserve special attention to ensure selection of the proper control. Constant horsepower motors require larger starters than either constant torque or variable torque motors of equal horsepower. Now, reversing and reduced voltage operations can be incorporated in a multi-speed motor starter. Now, synchronous motor controls. Now, if you look at the videos I've done already on motors, you'll see that I've mentioned quite a bit here on synchronous motor controls as well. So look in the electrical principles section in the playlist. Okay. Controllers for synchronous motors have 4 components. A 3-pole starter for the AC stator circuit, a contactor for the DC field circuit, an automatic synchronizing device to control the DC field contactor, and a cage winding protective relay to open the AC circuit if the motor operates too long without synchronizing. Synchronous motors require AC power during both starting and running, thus the main contactor is closed when the motor is operating. The DC winding of the motor is energized by the field contactor. As the motor approaches synchronous speed, 2 normally open poles on the field contactor make the connection for DC excitation, and 1 normally closed pole permits dissipation of induced field current through a resistor during any period of non-synchronous operation. For smooth synchronization, 2 conditions determine the instant that the DC field is energized. The rotor must be turning at the proper speed, usually 93 to 98% of synchronous speed, and the rotor poles must be lagging slightly behind state poles of opposite polarity. Several synchronizing devices apply DC to the rotor field. Special relay systems can automatically close the DC contactor when the rotor reaches the proper speed and the rotor and stator poles are in proper relationship. These relays will open if the motor falls out of step because of a momentary overload or voltage dip. Now, synchronous operation is automatically restored when voltage returns to normal or the overload is removed. In some cases, resynchronization may not be desirable from a safety standpoint. In such cases, the controller can be designed to disconnect power from the stator. Out-of-step protection is provided by a conventional thermal overload device. This device is energized whenever the motor is running without rotor field excitation. If during the start the motor does not synchronize within a given time period, usually 15 to 20 seconds, the OSB relay opens the main contactor. If the motor pulls out of step while running and does not resynchronize within the specified time, the relay will disconnect the motor. Okay. This protection is necessary because the cage winding has limited thermal capacity and will overheat in a short time at synchronous speed. Synchronous motors can be stopped quickly by methods similar to those used with induction motors. Okay. Now I'm going to stop here for a moment, and I'm going to stop talking, let you just read this through for yourselves, okay? Because I realize that some of you don't like reading. You look at a thing for 10 seconds and think you've read it. Okay. Now I'm just going to run this down to this point, and then I'm going to stop. Now we have here non-excited motors, so again, read this through for yourselves, okay? I'm not going to read this through to you. Okay, I just want to bring this here to a close if I can, and I'm trying to find a good point on which to do that, so just bear with me. Again, here is for you to pause on the video and to read for yourselves. Okay, let me just see if I can get the okay, right, that's where we'll stop. Okay, so I'm just going to bring here now. This is session 3 which I'm doing, so we're going to stop at induction motors, and I'll pick that up from the next session, which will be session 4. Okay, the reason why I'm doing this in sessions is because there's so much pages of it to be done. Okay, so I've stopped now on page 28. Okay, so I'll pick up on page 28 for session 4. This is session 3. Okay, right, I hope you found this useful. Okay, so what I'm going to do now, I'm going to stop there. Let me just go back up. And this is without me talking now. Okay, just go back and make sure that everything has been in view. Okay. Okay, just to make sure that everything is in view and that I have not missed anything when I was talking. Okay, that's good. Okay, we can stay there. Thank you. Okay, I'm happy with that. Okay, thank you. Right, we'll stop there now, and I hope you have had a good day. Okay. Bye for now. Bye-bye.